Good morning, ladies and gentlemen. All right, today we are doing Mountain Math set number 18. In front of us are the numbers that we'll need to use for this set. I'm going to go through problems 1 through 12 in this tutorial here. All right, so I have gone in and pre-filled some of the numbers to keep the video brief. Unfortunately, I tried to do the same thing with set 17 and the video was still 40 minutes long. And I think that that's just the nature of mountain math, and I think it expresses the importance of mountain math, how important it is to be practicing the skills that we are practicing on problems 1 through 12. Okay, so that is my soapbox speech for the day. Now, I am looking at two numbers, 20,989 and 21,980. Both of these numbers, when we go to add 100 and take 100 away, more or less add 100, we're going to see some big changes in these numbers. Nines are going to be changing to zeros and thousands places are going to be changing. But let's start with even and odd. I'm looking at 20,989. And I see that there is a 9 in the ones place. 9 is an odd number. Therefore, because that odd number digit 9 is in the ones place, it makes the entire number odd. Now I'm looking at 21,980. I see a 0 in the ones place. Anytime the digit 0 is in the ones place, we can be sure that this number can be broken in half, divided by 2 evenly. So therefore, it makes the number even. In word form, I have both of the numbers written out for you to check your spelling. Expanded form, we have a 2 in the 10,000s place. So that value of that 2 is 20,000. However, there's a 0 in the thousands place. You'll notice that I skipped right to the hundreds. I didn't put the 0 there. I have 900 plus 80 plus the value of that 9 in the ones place, which is 9. Expanded form of 21,980. You can see that I have a 1 in the thousands place, and I've written that in the appropriate place. The value of the 2 here is 20,000 because it's in the tens place. I do have a digit 1 in the thousands. There's that 1,000 plus 900 plus 80. And you'll see that I stopped there because there was a 0 in the ones place. I do not need to add in plus 0. Okay. All right. Adding 100 to a number that has a 9 in the hundreds place. The only place that that 9 has to go is to 0. So I've notated that there. But any time that you have a digit in the nines in the hundreds place that's a 9, you need to, 1, turn that into a 0 because that's the only place it can go when going up. And the thousands place also must go up at that time. 20,989 plus 100 is 21,089. You'll notice the same thing in 21,980. By adding 100, you're increasing that digit 9 by 1, and that means it goes to 0. Our digits go 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, and then it starts over. When that turns to a 0, the thousands place must also bump up 1 digit from a 1 to a 2. So adding 100 to 21,980 is 22,080. Now, taking away 100 is a very cut and dry strategy here, and that's simply going to the hundreds place and decreasing it by 1. So you'll notice that I've put an 8 into both of those hundreds places, writing the correct number there. Multiplying by 10, well, anytime you multiply by 10, simply add a 0 and put your commas in the appropriate place. 209,890. Over here, 21,980. Simply add a 0, put your commas in the appropriate place. 219,800. Again, the power of the zero is incredible, not to be undervalued. Put 2 zeros when multiplying by 100, and put 3 zeros when you're multiplying by 1,000. And put your commas in the appropriate place every 3 digits, or at the end of every period. Ones, tens, hundreds, that's the end of the ones period, comma. 1,000s, 10,000s, 100,000s, that's the end of the thousands period, comma. And then put your commas in the appropriate place for multiplying by 1,000. Okay. Comparing these two numbers, again, we're starting on the left-hand side and we're working our way over to the right-hand side of the number. And as we are doing so, we're looking for the first place value position that has 2 different digits. We cannot use the 10,000s place because they both have a 2. However, if we move over simply one place value position, we find our place value spot that has 2 different digits, a 1 and a 0. 1 is greater than that 0, making 21,980 greater than 20,989. Or if you're reading from left to right, it's 20,989 is less than 21,980. All right, looking at how many ones are in the tens place. In order to do that, you got to know where the tens place is. We're looking at the digit 8. If I have an 8 in the tens place, its value is 80. How many ones does it take to make 80? Well, it takes 80 $1 bills to make $80. So I'm going to assume that 80 ones makes 8 tens. How many tens are in the hundreds place? There's a 9 in the hundreds place, and the value of the 9 is 900. How many tens does it take to make 900? Or 10 times what number makes 900? 10 times 90 makes 900. We have the same 2 digits in 21,989 in the tens place and in the hundreds place, so we can simply transfer what we wrote down from 20,989 over to the right-hand side. All right, what's the value of the number 8 in number 2? We are looking at 684,391, and we want to know what the value of the number 8 is, or the digit 8. That 8 is in the 10,000s place. 80,000 is the value. The 3 is in the hundreds place. Its value is 300. All right, let's round these numbers to the tens, to the thousands, and to the millions. Tens place, 684,391. We want to round this number to the nearest tens place. What are we doing? Well, we're looking at the 9 because that's the number that we are deciding what to do with. Is it closer to 90, or is it closer to the next 100 up, which is 400? So let's take a look. We are going to cover up this number, and what we see here is 91. Now, our only options are 91, are 90, and essentially adding 100 to it, or making this 400. So what's in the middle between 90 and 100? That's 95. We see that we have a 91. Is 91 over here between 90 and 95, or 95 and 100? It's over here between 90 and 95. That means that to the nearest 10, this becomes a 90 and everything else stays the same. 684,390. 684,390. Now to the tens place. The thousands place. We're looking at 4,391. Well, we could do the same thing here. We can look at this as, well, we can either round 4,391 to 4,000, or we can round it to the next 1,000 up, which is 5,000. What's in the middle? 4,500. And where does 4,391 fall on this number line here? Is it between 4,000 and 4,500 or 4,500 and 5,000? Well, it's over here between 4,000 and 4,500, maybe tucked in right there or so. And that means that 4,391 is closer to 4,000. So when rounding this to the nearest 1,000, notate our 4,000. Everything else to the left stays the same, 684,000. Now we're going to round to the millions place. And here we are once again dealing with a number that is not containing a digit in the millions place. However, there is one, and that is a 0. So what do we have here? We have either 0, right? 0 millions, or 1 million as our options for rounding 684,391 to the millions place. Now we got to ask ourselves, what is in the middle between 0 and 1 million? Or what is half of 1 million is another way to ask yourself what goes in the middle. And when I ask myself that question, I find that 500,000 is in the middle between 0 and 1 million. Now, looking at our number, 684,391, where does that fall on this number line? Does it fall between 0 and 500,000? Well, no, it doesn't, because there is a 6 in the 100,000s place, and here there's a 5 in the 100,000s place. So it's going to be closer to, or in between 500,000 and 1 million, maybe somewhere around there or so, 684,391. So in this case, we're closer to 1 million. 684,391 rounds to 1 million. Taking a little bit of a different approach on rounding numbers and not just relying on you understanding that digits to the right of the place value position that we're rounding, the 5 or more, or let it soar, or 4 or less and let it rest. This number line illustrates what that saying even means. I'm finding that as I'm helping you guys in Zoom, that the number line system is helping you a lot more than me just saying, well, is it 4 or less, or is it 5 or more? So I'm going to stick with this number line strategy here. Okay, all right. Numero tres, number 3. We're looking at 91. Is 91 prime or composite? Now, it's an odd number, so I know that 2 is not a factor, but I do know that 1 times 91 are 2 factors, 1 and 91, that make 91. And now I got a couple other options here. I can get my multiplication table out, and I can I can go on a hunt. I can look in my multiplication table and look at my multiples, right? So we're looking for the multiple 91, and then we're going to look for the factors that make that 91. And so I'm kind of scanning about, right? Looking for a 91. These numbers aren't even 91. I'm just looking for one. Ooh, there's 90. Boom, 91 right there. 7 times 13 is 91. So therein lies the purpose of this 15 times 15 multiplication table, because that was really helpful. 7 times 13 is also 91, therefore making this number automatically composite. But I don't want to finish yet, because I'm curious. I'm curious if numbers like 3 and 4 or 6 might also be multiples of 91. And so I'm going to do some long division to figure that out. If you're ever wondering if a particular factor, especially your 3s, your 4s, 6s, 7s, If you want to find out if those are multiples, use long division and divide. So we have 9 divided by 3, and we can do that. That's 3. And we multiply 3 times 3, get 9, subtract 1. 1 goes into 3, 0 times 3 times 0 is 0, and we have a remainder. So 3 is not a factor of 91. We can try 4, but 4 is often connected to 2. So we can see if we can get close here. 4 times 2 is 8. 1, bring down your 1. 11 is not going to go even. We're going to have a remainder of 3. So 4 is not a factor. Let's try 9. No, 9's not going to work because 9 times 10 is 90. 9 times 11 is 99. That's going to skip over. So I think right now we can be fairly confident that our factors for 91 are 1 and 91 and 7 and 13, making 91 composite. So we have 1, 7, 13, and 91. All right, cool. Number 4. Greatest common factor, children. The multiplication table is going to help you out here as well. So go ahead and make sure you have it on out if you are pausing this tutorial as you are working and then checking your answers. So we have 25 and 35 as our numbers. So I know out of the gate 1 times 25 and 5 times 5 are the factors of 25. 1, 5, and 25. Then we have 35. I know 1 times 35 and 5 times 7 are my multiples for 35. That's some real nice numbers to work with there. Guys, if you're ever unsure, use your multiplication table to help you find the multiple that you're trying to find the factors for. Okay, factors are in the black and all the multiples are in the middle here. Okay. So in listing out the factors, we have 1, 5, 7, and 35. Both of these are odd numbers, so I know 2 is not a factor of either of them. Greatest common factor. Well, let's see. What do we have in common? We got a 1 and we have a 5. The greatest common factor of 25 and 35, by putting a box around it, is 5. And we have 2 common factors. Okay, it's very helpful if you're listing out the factor pairs first and then you're listing the factors from least to greatest. All right, list the multiples of each number on the number line. So to find the multiples of 3 and 5, this is where 3 and 5 are your factors and you're looking for their multiples. Okay, all the numbers, and you're multiplying 3 times anything. You got your whole list up to 15 here for 3 and for 5 as well. So I'm going to list at least 8 for 3 and 5. 3, 6, 9, 12, 15, 18, 21, and 24. And then we have 5, 10, 15, 20, 25, 30, 35, and 40. Okay, now these are the multiples. Now we need to put a star around the least common multiple. Okay, the smallest multiple that 3 and 5 share. And as I go down the list, no 3s, 6s, no 9s, no 12s, no 15s, yes. And now I'll put my star around my least common multiple. Okay, all right. So do remember that numbers 4 and 5, greatest common factors, helping you to put fractions into simplest form. And then number 5, least common multiple, is helping you to locate a common denominator if you're ever dealing with 2 fractions that have a different bottom number. All right, complete the pattern. So we got 1, 4, and 7 dots, respectively. So 1 to 4, well, 1 times 4 is 4. So I could be a possibility. 4 to 7. 4 times 4 is not 7. So I know it's not multiplying by 4. I know we're not subtracting anything because the circles are getting larger. I know we're not dividing because the circles are still getting larger. So that leaves me with addition. 1 plus what's going to get me 4? And is that the same thing for 4 plus something giving me 7? 1 plus 3 is 4. 4 plus 3 is 7. So I can assume that my rule is going to be add 3. Okay, what are the features? Well, we are not dealing with numbers. We're dealing with dots or shapes. So this is a non-numeric pattern. Yes, it is using amounts of or quantities of circles. However, the features, what we are looking at, those are not zeros. Those are simply circles or shapes, non-numeric. So now we need to figure out the 10th and 15th number in our pattern. Well, let's find out one. If I add 3 to 7, I'm going to get 10. If I add 3 to 10, I'm getting 13. Adding 3 to 13, I'm getting 16. Adding 3 to 16, I'll get 19. Adding 3 to 19, I'll end up with 21. Adding 3 to 21 to get that 10th number, we can just keep going with it. So adding 3 to 21 gives me 24, that's 6. 27 is 7. 30 is 8. 33 is 9. 36 dots will be the second, or the 10th amount of circles in the pattern. What's the 15th? Well, we can keep going. 36 plus 3 is 39. Then we have 42. That's number 12. Then we have 45. That's 13. 48 is 14. And 51 is the 15th number of shapes in the pattern. Okay? So that was the hands-on. I'm going to simply continue the pattern. I'm not using any multiplication strategies here. I'm simply listing the next event as it comes and then finding the 10th and 15th number there. All right. So number 7, let's take a look at what we're dealing with here. In number 7, it says 18 is 9 times as many as what? So since we have a number in word form, 18, and then right next to it, the word is, that means that 18 is the answer. Okay, so 18 is, we're working backwards here. 18 is 9 times as many as what? As 2. 2 times 9 is 18. And then you can draw your array down here at the bottom. Number 8, I'll bring this a little bit closer again and do a little read. We got our character here, and our character this morning is Meg. Meg eats 9/15 pieces of a granola bar. It's an awfully big granola bar to be cutting into 15 pieces. And Sarah eats 3/5 of a granola bar. Do they eat the same amount? Okay, so this is asking, is 9/15 the same as 3/15? And there's a way that we can do that. We can take both of our fractions. We have 3/5, we have 3/5, and we have 9/15. So 3/5, that fraction is in simplest form, okay? And I know that because the only factor that 3 and 5 share, if I list them out, the factors of 3 are 1 and 3. The factors of 5 are 1 and 5. The only factor that they share is 1. And with a factor of 1, that is not going to change this fraction via division. Okay, 3 divided by 1 is 3, and 5 divided by 1 is 5. 3/5 is already in simplest form. Now, how about 9/15? So 9/15 is not in simplest form. I know they share a factor that's greater than 1. And I believe that that factor, that greatest common factor between 9 and 15 is going to be 3. The factors of 9 are 1, 3, and 9. And the factors of 15 are 1, 3, 5, and 15. There's that greatest common factor 3. Just like number 4, we'll put a box around it. And now we'll do something with it. We are going to divide 9 divided by 3 and 15 divided by 3. 9 divided by 3 is 3, and 15 divided by 3 is 5. And guess what? 3/5 and 9/15 are equivalent, boys and girls. We have landed on a fraction finally, at least in number 8. This isn't number 12, but I showed my work on a separate piece of scratch paper because I'm never sure if I'm going to have enough. So in the box here, I can write 3/5 and 9/15 are equivalent. You could write equal, but equivalent when talking about fractions is the appropriate way to express that the two or more fractions are equal to each other. 3/5 and 9/15 are in fact equivalent. All right, was there a second part to this question? Draw the fraction of granola bar that Meg eats, right? So she's eating 15 pieces, right? So let's draw this. Granola bars tend to be rectangular, so I can draw this out. You know what? And for giggles, we can draw out her buddy's granola bar too. What was her buddy's name? Sarah. So Meg ate 9/15. So this granola bar needs to be broken up into 15 pieces because she ate 9 out of 15 of them. Okay, so we're going to try to squeeze in 15 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. And then just for giggles, we'll draw out Sarah's. Hers was in 5 pieces. So 1, 2, 3, 4, 5 pieces. Oh, that's 6 pieces. Oh no. So we'll go 1. She ate 1 piece. Okay. And then she ate 2 pieces. That's our piece line right there. Right. She ate 3 pieces. And then we'll 4 and 5 pieces left. I am so sorry for that terrible drawing. All right, so there's 3 pieces. And then we have Meg eating her 9, 2, 3, 4, 5, 6, 7, 8, and 9 pieces. And if I would have drawn this exactly, you'd see that 9/15 and 3/5 are the same amount of pieces. So we have piece 1 here, 2, 3, 4, and 5, and then all the way up here. So as I look at this, I've drawn Meg's 9/15 and I drew Sarah's just to show you that 3/5 and 9/15 are the same, minus my really atrocious looking drawing there. Okay, all right, that's number 8. Number 9, adding and subtracting. Well, we're adding 10,256. We got a bunch of zeros, and we are adding 256 to it. This is mental math. This is 10,256. However, when subtracting, it is a much different story. We have zeros across the top, making all the digits on the bottom larger. So we're going to have to start over here at this 1. And we're going to start here, and we're going to borrow that 10,000 and give it to the thousands place. And we borrow 1 10,000. That's 10 1,000s. that end up over here. However, we've got to borrow from this string of zeros. So what we're going to do is cross that 10 out, make that a 9. This becomes a 10. Good. Oh, but we're still not done because we need to borrow from this 10 again to make 10 in the tens place. So that becomes a 9. This becomes a 10. And we realize, oh, we've got to borrow from this 10 to make this 0, 10. So this becomes a 9, and this becomes a 10. We have nothing left to worry about as we move down our place value position, so this 10 stays the same. So essentially we have a 10, we have a 9, we have a 9, we have a 9, and we have a 0. 10 minus 6 is 4, 9 minus 5 is 4, 9 minus 2 is 7, 9 minus 0 is 9. 9,744. Okay. We're going to multiply 255 and 3 and divide those same two numbers. 255 times 3, 5 times 3 is 15. Two-digit number. Put it over here to the right-hand side. Circle it. Got to do something with it. We're going to put that 5 down, and we're going to regroup that 110, bring it over to the tens place. Now we're going to multiply 5 times 3 again. We can get 15 again, but we're going to add this 1, and we're going to make that 15 16. Two-digit number. Put it over here. Circle it. Remind you, got to do something with it. Put down the 6. Regroup the 1. And when I say that, it's like, what are you going to do? Are you going to put down the 1 or put down the 6? What are you regrouping? That's why I ask you to write that over there on the right-hand side. We're left with 2 times 3, and that is 6 plus 1 gives us 7. 255 times 3, or 255 plus 255 plus 255 gets us to 765. All right, I've got my numbers kind of cramped in here. I am going to be moving my long division over to a larger piece of scratch paper just so that I can ensure I have plenty of space to do my work. 255 divided by 3. I'm noticing that that 2 is smaller than the 3, so I'm skipping over and looking at 25 divided by 3 first. Let me rewrite my problem. So again, 2, you cannot do 2 divided by 3, okay? 2 cannot be put into 3 groups. There's not enough. It's 0. It is not mandatory that you put a 0 there. So just scoot on over to 25. That's the first place value position that makes your number large enough so that you can divide. 25 divided by 3, the closest I can get is 8. Then I multiply. 3 times 8, 24. 25 minus 24 is 1. Bring down my 5. My new division problem is 15 divided by 3. 15 divided by 3 is 5. 3 times 5 is 15. And when I subtract, I get 0. No remainder. My quotient or my answer is not 0. My answer is 85. Okay. Put that in that box there. Okay, that's number 10. All right, number 11, filling in the missing number. We have 561 plus 12 on the left-hand side of the equal sign, and then we also have 560 plus some number plus 3, and we got to make sure that those numbers are equal. Now, 560 and 561 are not equal. So right away, what I notice between the left-hand side of the equal sign and the right-hand side is that I'm adding 13 to 560. That's what I see because I have a 1 and a 12, right? That 1 and 12, that makes 13, okay? Trying to make these two numbers even. That's my strategy that I'm going for right now. I'm saying, hey, instead of 561, why don't we make this 560, okay? And then on this side of the equal sign, we'll keep it 560. And when we do that, we have this 1 in the ones place left over, okay? And we have the 12. That means that we are adding 13 to 560. We do that, we get 573. Or another way, 561 plus 12 is 573. We need to make 573 out of 560 and 3 here. So that means that this missing number has to make 13. 3 plus what is 13? 10. So we have 560 plus 3 plus 10. So our missing number is 10. There we go, number 11. All right, number 12, 8/9 and 9/10. So very similar to set 19, set 18, where we are able to use our division strips. So by using our division strips, we're going to find 8/9 and we're going to find 9/10. So if I'm looking here, we're dealing with 9ths and 10ths. So this area here, okay? So 8/9, we have 1, 2, 3, 4, 5, 6, 7, 8, just like yesterday, or set 17, I should say. And then we are looking for 9/10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, here we are, so close. And so I know that 9/10 is just barely greater than 8/9. 9/10 is just barely greater than 8/9. Or reading left to right, 8/9 is just barely less than 9/10. Are the fractions equivalent? No, they're not, because 8/9 is smaller than 9/10, or 9/10 is greater than 8/9. And then it says for us to make them equivalent. In order to do that, we need to find the least common multiple. Okay, and here's why, guys and girls. We are looking here, and we can look to see if anything with 9ths and 10ths is equivalent anywhere along these lines here. And I do not see any equivalency. None of the lines match up between 9ths and 10ths. And when that's the case, we have to use least common multiple. So we're going to list out the multiples for 9 and 10. So we have 8/9, and we have 9/10. And then we have our, we know we're going to be multiplying by something eventually. When we find least common multiple, we know we're going to be multiplying by some number. Whatever we do to the bottom, we do to the top. And then that's going to make our new fraction, where in these boxes, we're going to have the same denominator. Okay. But let's list the multiples first. We have 9, 18. Look, and we're comparing multiples of 9 and 10, and so we're trying to find the first multiple of 9 that has a 0 in the ones place. Okay, and some of you may already know this. We have 45, 54, 63, 72, 81, and 90. There it is. Okay, and then we have 10, 20, 30. All the multiples of 10 are going to have a 0 in the ones place. 40, 50, 60, 70, 80, and there is 90. The least common multiple of 9 and 10 is 90, and I should be putting a star around that. My favorite direction in mountain math. So we know that our least common multiple is 90. That means our common denominator, kids, is 90. But what do we do to 9 to make 90? Multiply it by 10. What you do to the bottom, do to the top. 80 90ths. And then we have 10 times something is 90. That's our 9. 9 times 10, 9 times 9, 81, right? 1/90th difference between 8/9 and 9/10. Okay, 1/90th, very tiny. how do we make them equivalent? We got two options. We can turn 80/90ths into 81/90ths, or we can turn 81/90ths into 80/90ths. On set 817, I'm pretty sure I added, so this time I'm going to subtract. I want to make 81/90ths the same as 80/90ths. That means I just need to take 1/90th away. 81/90ths minus 1/90th is our 80/90ths. Okay, so basically what I did is I changed 8/9. Okay, excuse me, I changed 9/10 to 8/9 is essentially what I did. But for our purposes, if you're understanding that when you've got to make two fractions that are different or not equivalent, first you list the multiples, find the the least common multiple, making that your denominator. If you can get to that step right there, you are doing fantastic, especially without any of the conversation that would normally be happening in the classroom and you listening to me using the language of fractions. If you can get yourself to the point where you're putting a star around the least common multiple, I want you to give yourself a pat on the back and feel comfortable that you do know that. If you're still struggling with that, please send me an email. Okay. So I did make them equivalent. You can draw your fractions, add them, subtract them if you can. Okay. All righty, boys and girls. That is Mountain Math set number 18, 1 through 12. All right, boys and girls.